Hi guys, I am back again. Today we are going to discuss the drawing of shear and moment diagram for loads of uniformly distributed over the inlet span beam and some concentrated load applied to it. So this is our third lecture. The first lecture was beam loaded with all concentrated loads. Second lecture was all about beam with uniformly distributed load. And then now we are going to draw the shear and moment diagram for beam with uniformly distributed plus concentrated load. Okay, let's say this is 10 kilonewton per meter, and then we are going to one concentrated load here. Let's say this is 80 kilonewton at 2 meters. Let's say this is at 8 meters. So we are going to solve for the reaction first. So the reaction here, let's solve. We are not going to show the solution for the reactions anymore because I assume that you already mastered the solution for RA and R. So we are going to make a test. So 80 multiplied by 2 plus 10 multiplied by 10 divided by 10. So I think R will is 66. And then let's say 180 less 66 equals 140. So we have a reaction of 140 at A and reaction at B of 66 kilonewton. We are now ready to solve or to draw the shear and moment diagram. First, we are going to draw the shear diagram. So again, we are going to draw the horizontal line here, showing the length of the loop. So first, we have 140 upward, 140. At 2 meters, we have a concentrated or uniformly distributed here. So we are going to consider only this portion at 2 meters span. So that will give you 10 multiplied by 2 is 20. That means 114 minus 20. So since this is rectangle, the shape will be triangle like this. And that will give you 114 minus 20 is 24. Let's check. 114 minus 20, 394. And then at this point, at 2 meter, we have an 80 downward. So that means we're going to subtract this 80 from 94. So minus 80. That will give you 40 kilonewton. So we have 40. So again, 114 down upward, then downward force of 10 multiplied by 2. So 114 minus 20, that's 94. Then we have downward of 80 here, that's 14. And then we are going to consider the 8-meter span of the beam. So that means we have a force downward of 10 multiplied by 80, that's 40 positive minus 80 negative, that will give you 14 minus 80, negative 66. So we have a triangle here. Here. 66 negative plus 66, that is 0. Oh, no, should be. Okay, so notice that we have a shear diagram of trapezoid shape and triangular shape, and at a point in the beam we have 0 shear, equals 0 at this point. What is important about this point is, at this point, the maximum moment is located. So it is important that we know the location of this point, the location of the maximum moment. So we are going to label this as x. X. And this is 2. And the whole part here is 8 meter. We don't know the value of x. So first thing is to solve for the value of x. We are going to use the ratio and proportion technique to solve for the value of x. So it's better for the sake of simplifying the solution in finding the value of x, we have this. So this is 14 and this is 66. The whole is 8 meters. So our solution is like this. X is to 14 equals, we're going to add this, consider the whole triangle. 14 plus 66, that is 100. So no, 80. 8 meter is to 80. Let's check. 14 times 8. Okay. That will give you the value of x as 1.4. Okay? So is it clear? So we isolate this portion for simpler illustration. So this 14, we don't know this value of x here, this part, and then this is 8 meter. For x is to 14 as equal to 8 meter is to 80. That will give you the value of x as 1.4 meters. So we know now the value of x here, which is 1.4. We can now draw the moment diagram. Okay. Drawing the moment diagram here. First is we have zero moment here for in supports, moment equals 0. And then we are going to solve for the area of this trapezoidal shape of the shear diagram. So we know that the area for trapezoid is 114 plus 94 multiplied by 2 divided, divided by 2. So that will give you 114 plus 94 is 2 over 2 is 208. Okay. Again, this is sloping line or triangular line. So we have a part. This is 200 feet. Okay. Next is we are going to get the moment here. Again, it is obvious that at this point for x is equal to 1.4 from here, the moment is maximum. So 208 plus the area of this triangle. So 14 times 1.4 divided by 2, 9.8 plus 208. That will give you 217. Ladder curve. 217. And we have a negative area here. We know that this distance is 8 minus x, that is 8 minus 1.4, that is 6.6. So we can easily solve now the area. 6.6 multiplied by 66. Divided by 2. So this area, 66 multiplied by 6.6 divided by 2, that is negative 278. So 217.8 less 217.8, that will give you 0 moment at the end. Here. 0. Okay. So in this lecture, we learned one important thing to remember in drawing shear and moment diagram later on. And this thing is drawing the moment diagram when in the shear diagram we have to determine an unknown distance x so that we can solve for the value of that moment along that portion of the beam with unknown value of x here. We use the ratio and proportion technique in solving for the x here, as we have shown here a while ago. So as usual, we use the area of the shear diagram to solve for the magnitude of the moments along the points of the beam. So, the same way the previous lectures, you need to have an accurate shear diagram to get the accurate moment diagram. Okay? So, there are many modifications of this type of problems. You can add concentrated loads here, or you can add distributed
over the entire span. You can have uniformly distributed here and one distributed. The concept is always the same.
So that's all for now. Next video will be discussing shear and moment diagram for cantilever beam. Cantilever beam is described as one end is fixed, the other end is fixed. See you next time.